All right, in this video, I'm going to be talking to you about linear transformations. But before we get into that, I need to just show you some properties of matrix multiplication. So I'm just going to list them out real quick right here. So really what I'm trying to tell you is that matrix multiplication distributes. Now, I will also, probably also add on that if we right multiplication also distributes the way you would expect it. Okay. And then, multiplication by a constant is also going to kind of work the way we expect. So I just need to throw those things out there so that I can talk to you about linear transforms. So our definition of a linear transformation is a function that observes these two properties, okay? That if we take f of a sum, it's the sum of taking f of the individual pieces of the domain and then adding them together. And that if we are going to take f of a number times some element of the domain, that result is going to be that same number times f of that element of the domain. Okay? And what I'm going to propose is that matrix multiplication defines a linear transformation. Okay? So I'm going to prove that for you. But first, I'm going to point out that in this class, we're going to really be interested in functions that take in a vector and give you back a vector. So I'm going to kind of just put the little adornments on these things, just to remind you. So how am I going to prove this? Using the properties that I just told you. Okay, so let's consider what happens when when I put, say x plus y into f. Well, f of x just takes x and it multiplies it by a on the left. So I'm going to have x plus y instead of x, right? And because of the distributive property, I know that this is going to be ax plus ay, which is, let's see if I can fit this in my shot, f of x plus f of y. Okay, we got it. Okay, and then I need to have, my matrix or my scalar multiplication property. So f of k times x is going to be a times kx. Which, okay, I didn't tell it to you exactly like that in the properties or whatever, but this is going to be k times ax. And that's why matrix multiplication is a linear transform. Now, we're actually, in this class, I think we're going to take it a step farther and say that any linear transformation can be expressed as a matrix if we're mapping from, some vector space to another vector space. But I think we'll deal with that later. We'll attack that at a different time. So let's do an example now. So I'm going to start off with a matrix and say I'm going to define a function t of x to be a times x. And I'm going to ask you a couple of questions. I think the first question I would ask is find the value of t of the vector 1, 1. Okay. Now, I could also take this a different direction and ask you about the domain and codomain of this thing, and maybe I'll deal with that when I'm not looking at a 2x2 matrix, when I'm looking at something more interesting, and maybe you'll be able to see a little easier where I'm getting these things from. But first I'll ask you to find t of 1 and 1. Okay, well, t of the vector 1, 1 is equal to a, 1, 2, 3, 6, times the vector 1, 1. And I'm going to get, okay, 1 times 1 plus 3 times 1 is 4. And 2 times 1 plus 6 times 1 is 8. Okay, so that's easy enough. That's just us practicing our matrix multiplication. And what you'll see with this lesson, I'm not going to tell you anything too specific about linear transformations yet, because we'll be studying these throughout the linear algebra course. Really, this is just going to be a way for us to practice our matrix multiplication and our row reduction, those two skills that we've just kind of learned. So the next question I might ask is find a value of x for which p of x is equal to the vector, how about 0, or 1, 0? How about that? All right. And this Okay, right now I'm trying to convince you that solving for a vector in solving really for a matrix in a matrix equation is going to be the same as solving a system of linear equations. We're going to use row reduction to solve it. Okay, so I'm trying to convince you this is actually the same thing. So I'm going to set up, I'm going to have 1, 2, 3, 6 times some vector x, which is going to have to be a two-dimensional vector, and that's going to come back and equal 1, 0. Well, what that means, if I actually do the matrix multiplication on the left, I'm going to have 1x1 plus 3x2 and 2x1 plus 6x2. That's what I get when I do that matrix multiplication. And I know that that has to be equal to the vector 1, 0. But what we're used to is saying like equals 1 and equals 0 individually. And what do you know? This is a system of linear equations. Two equations, two variables. We know how to attack this, right? We write ourselves an augmented matrix. That should be a 3. 3, 6 augmented with 1, 0. And we can row reduce this thing to solve. Okay? So I'm going to take 2 copies of row 1 and subtract that from row 2. And I'm going to have 1, 0, 3, 6 minus 2 3's, also 0. 0 minus 2 1's is negative 2, and I didn't change the first row. But wait a second. I see this, and I know I am in a no solution scenario. So there is no x. Okay, that's just not going to be possible. And we'll talk much more about the range of a matrix and what is and isn't possible at a later time once we have more tools under our belt. But at this point, we're just going to say there's no x that can be 1, 0. And then the last question I want to ask you with this example is find the value of x so that t of x is equal to the 0 vector. And I'm realizing that maybe in this set of videos we haven't talked about the 0 vector, so maybe I'll define that up here. So that's the 0 vector is the vector with all zeros. Okay. And we're just always going to assume it's the appropriately sized 0 vector. In this case, the 0 vector is going to be the two-dimensional 0 vector, so 0, 0. Okay, but we'll be dealing with the 0 vector quite a bit in this class. And in the textbook that we kind of work out of, they use the 0 vector. They use a theta with a vector. I think they use bold for vectors, but they use a bold theta. So we'll use that as well. All right, so we're going to find a vector x so that t of x is equal to 0. And in part B, the previous question I asked, we saw that we can solve for a vector in a matrix equation by using row reduction. Okay? So I'm going to go over here, 1, 2, 3, 6. I'm going to augment this with 0, 0 because I want to find a vector x for which a times x equals that 0, 0 vector. And that will be, okay, so I'm going to start. I'm just going to row reduce again, and I know how this is going to go because I already did this once, right? And I'm over here, and I've got 0, 0, 0, and that is a sign that I might be in an infinitely many solutions situation, and I am. And so what I'm going to say is that, okay, this is as far reduced as I can go. I can't do anything else. So I'm going to say that what this means is that 1x1 plus 3x2 equals 0. Okay? So if I wanted to express all of the possible vectors for which t of x equals 0, I'm going to say, well, x1 is negative 3x2, and, x is equal to negative 3x2 and x2. Or I could factor that out, and I could say it's just some number x2 times negative 3 and 1. Okay, so negative 3, 1 would be an example of a vector that t of negative 3 and 1, that will be 0. But if I chose x2 with some other number, like, I don't know, maybe I'll make it negative 2. So, for example, I could say x equals 6 and negative 2. And I might suggest that you pause the video right now and go and multiply a times negative 6, or 6 and negative 2, and see that that does give you back the 0 vector. But I'm going to move on. All right, now the last thing I need to tell you about right now is the domain and codomain of these linear transforms that we're defining with matrix multiplication. So the first example we looked at was a 2 by 2 matrix, okay? And it was pretty easy to see that, you were going to have to multiply by a 2D vector and your two-dimensional vector. But what if we had a matrix that was not 2 by 2, right? Suppose A is m by n. So maybe I'll switch up the color a little bit. So suppose A is an m by n matrix. Okay? That means that, AX is going to be a matrix multiplication of, okay, A is an m by n, and X is going to have to be an n by 1, right? Because we need these two numbers to be the same. And then that's going to give me back a vector we'll call B. And that will be an m by 1 matrix. So this function, f, is a function that takes in an n-dimensional vector, right? X is an n by 1 matrix. So it takes an element of Rn, and it gives us back an element of Rm, because the resulting matrix, the vector B, is an m by 1. Okay, so if we were to, look at an example here. And if we have, g of x is this matrix M times x, and matrix M is, 1, 2, 3, 4, 0, 1, 0, 1, and 1, 1, 3, 3. Okay. That'll work. Okay, G, the domain of G, that's the type of vectors that we can put in for x. Well, if we're going to put in an x and the matrix multiplication is going to be well defined, then I need, when I go to do the matrix multiplication, I need there to be kind of an equal number of terms on that row as this column. So I'm going to need this column to have 3 entries in it. So I'll need that to be x1, x2, x3. So I can conclude that the domain of G is R3. And M being a 4 by 3 matrix, if I multiply a 4 by 3 by a 3 by 1, I will get back a 4 by 1 matrix. So that means that the codomain of G, which is kind of like the space that the range lives in, the type of things that we will get back from this function, the codomain of G is going to be R4. And I think at this point, this is all I need to tell you about linear transforms. Okay, we'll be revisiting this topic 2 or 3 more times in this course, in this video series. So, at this point, all we need is just kind of like the introduction. What's the domain and codomain? How are we going to evaluate actual, values of the function? And how can we kind of solve backwards for, a particular vector in the domain, given a vector in the range, possibly. So that's all.